Okay, hello and welcome. Today we're going to talk about the life cycle of stars. And this corresponds with Chapter 26, Section 3, which is pages 844 to 848 in your textbook. Just a few key points to talk about. First of all, the life cycle of a star follows a pretty predictable pattern, and we're going to talk about that main sequence again on the HR diagram and how stars find their way there and what can happen to them at the end of their life. The majority of the star's life, though, is spent in a pretty stable state, and the mass of the star will determine how long it will live as well as the nature of its demise. Okay, the first big topic in this section is the birth of stars. Where do stars, how do they form? Where do they come from? Well, stars form when a contracting cloud of gas and dust becomes so dense and so hot that nuclear fusion begins. These clouds are known as nebula, and the text says it's a large cloud of gas that's spread out over a large volume of space. So it's a lot of gas in a big area. Here's some examples of those nebula. This is the Cat's Eye Nebula. Okay, here's the Crab Nebula, and you'll notice that it's not like a big ball of gas per se. In fact, there are areas that are more dense and less dense, and it's in the areas that are more dense that gravity starts to pull that gas together to form a star. Okay, so gravity pulls the nebula's dust and gas into a denser cloud that contracts, and therefore the gas heats up. You should remember that from our PHET simulator that we did at the start of this unit. The beginning, this young star, is called a protostar, and as that protostar continues to contract, its internal pressure and temperature continue to rise. Once the temperature and pressure reach the right amount, we have fusion begin and a star is born. Just one last nebula to look at here. And you should remember from our previous lesson that the outward pressure of fusion and the sort of inward pressure or force of gravity is going to be maintaining this balance, right? And that's the stable state that we're talking about at the start of the presentation. Point number 2, what determines how long a star remains on the main sequence? Well, it's the star's mass. Depending on how dense that area was within the nebula the star was born from, there's going to be more or less matter available. And so the amount of dust and gas available will basically determine how large or how massive a star will be. Larger stars, massive stars, have larger cores and produce the most energy. And low mass stars, something as small as say 1/10 the mass of our sun, produce smaller, cooler stars that live for a longer period of time. So as we discussed in the previous lesson, it's hydrogen fusion at the core of the sun that's essentially the powerhouse for the sun and for any star for that matter. Well, eventually that fuel, that hydrogen, can run out, and that dwindling fuel supply in the star's core will ultimately lead to its death. And there's a few options for that star depending on the mass. One is to become a white dwarf, the second is to become a neutron star, or the third is to become a black hole. So if you take a look at the image below, you can see that all stars, on the left there, you see their sort of starting size. All stars will kind of make the first step in the same direction. They'll leave the main sequence and they'll move off of it. And what happens is that the temperature gets so hot inside the core that you'll start to have a shell of hydrogen outside the core that also begins to fuse. And when that's happening, it blows off a little bit more energy. And so the star has to restabilize. And to do that, it actually grows larger. And it does slightly cool, as you can see here, based on the color, right? It's moving to a red, the red side of the spectrum, so we know the star is getting cooler even though it's actually getting larger. On the right, you can also see the 3 possible outcomes for stars, and you can see that low to medium or average size stars will end as white dwarfs, larger stars will end as a neutron star, and then the largest of stars will actually end as a black hole. Okay, so lower and medium mass stars will be hot enough to fuse hydrogen and helium, but once those are used up, fusion slows to a stop, and there's less outward pressure, and then the star will basically collapse upon itself. Now that dying star will be surrounded by a glowing cloud of gas, and that's called a planetary nebula. And the dying star will then blow off much of the mass, and a white dwarf will remain. Now, a white dwarf would be something that's roughly the size of the Earth, but still has the same density as, for example, our sun. So this faintly glowing ball will basically be cooling for roughly 20 billion years, which is longer than the universe has been around to begin with. So we haven't actually had that happen yet. And those are located like in the sort of central bottom part on the HR diagram. Now, high mass stars, stars that are at least 8 times the size of our sun, will actually be hot enough to fuse other elements as well. And so you can see in the chart here that we'll have hydrogen, helium, carbon, oxygen, silicon, and eventually iron. And it also gives you sort of a duration about how long the star will be able to continue to fuse those various elements. And you can see that once silicon is fused into iron, the star has about a day to live. And when the core collapse begins, it takes less than a second, excuse me. So again, we're looking at stars that can fuse more elements, and they are going to become larger, and they become supergiants. Now, the collapse of that core of the star is known as a supernova, and that can actually outshine all other stars in its galaxy. It's that bright, it's that loud and violent. All right, I've got that big yellow arrow pointing right at iron, atomic number 26, and we just said that that's basically the heaviest element that can be created inside the core or inside a star. So the question then is, where do all the other elements come from? Well, they come from those supernova, because that explosion is so violent and so large, it actually can fuse all of the heavier elements that you see on this periodic table. And those, of course, that are going to be blasted out into the galaxy. So all of the atoms inside your body and inside everything else here on Earth actually came from stars or from the explosion of a star. So following the supernova, there is a core that remains, and if that core has the mass of less than about 3 times of the sun's mass, it'll actually become a neutron star. Now, neutron stars are smaller than white dwarfs, but they're also far more dense. And the text said that a spoonful of neutron star would weigh about the same as 1 billion tons on Earth. As they contract, they actually begin to spin, and that spinning can become increasingly more rapid. Those neutron stars emit steady beams of radiation in narrow cones, and because it's spinning, it appears to be pulsating, which is why they're known as pulsars. These strong pulses of radio waves can actually be detected here on Earth. Very massive stars have a different fate. If the core after a supernova is roughly more than 3 times the sun's mass, then the gravitational pull is very strong, and that gravity causes the core to collapse beyond the neutron star stage. So it's becoming smaller and even more dense. Eventually it becomes so small and so dense and has such gravity that nothing can escape a black hole, not even light. So if light can't escape from a black hole, then they're probably pretty difficult to see. And so one way that we can detect these, though, is to see, if you look at this image here, you can see that the black hole itself is actually bending the light from distant galaxies. It's almost like you're looking at a candlelight at the bottom of a glass. We're going to actually return to this image when we talk about gravity and the bending of space and time in the next unit. Okay, I hope that was helpful. Next time we'll be talking about electromagnetic waves in more detail, but if you have any questions now, ask them in class. Take care.